So today is all about getting you ready for sketching graphs of functions. And the new part that you're going to do is the calculus part. But there's a lot of stuff that you learned back in algebra about graphing functions that we just expect you to remember. So we're going to go over some of those things. We'll start with polynomials. So if you're going to graph a polynomial, let's see. Well, I sent it to you in the email this morning, but let's see. I had it in there. Let me copy it and I'll post it again. Control. There you go. Thank you. So if you're graphing polynomials, we always expect you to first off decide what the domain of your function is. So polynomials are friendly. The domain is all real numbers and they don't have any asymptotes. So those are things that we expect you to know. Do functions have asymptotes? What is their domain? Then when you see a polynomial, you look at the degree. If there is even degree, the ends go in the same directions, either up or down. And if there's odd degree, the ends go in opposite directions. And the right end always goes the way of the leading coefficient, because the limit as x approaches infinity is equal to infinity. If your leading coefficient is positive, it's equal to negative infinity if your leading coefficient is negative. And then we have some information about zeros. If you write it in factored form, you know it's going to cross the x-axis at any zeros that have odd multiplicity, and it's going to touch the axis at zeros that have even multiplicity. So let's sketch one. And the one I chose is f of x equals 3x squared x plus 4 to the third power. So first thing I think about is the degree. The degree of this polynomial is 2 plus 3. 5, which is odd. That means the ends are going to go in opposite directions. Leading coefficient is positive. That means the right end is going to go up and the left end is going to go down. So I have kind of an idea of what it's going to look like already. I have 2 zeros. I know it's going to touch the axis at 0. And it's going to look like just a happy parabola sitting there. I know that it's going to cross the axis at -4, 0, and it's going to look like a cubic function there. It's going to flatten out. So 1, 2, 3, 4, right here. And right here. And we got a bonus in this one because we also know where the y-intercept is because it goes through the origin. It has to start down here. It has to go up. It has to touch. And then it has to go on into infinity. Right now, that is as good a graph as we can do. Now you're going to learn to figure out where this little turn is and about concavity and where it's increasing and decreasing. That's what calculus is for. But if you can get this far, then the calculus is going to be easy. Questions so far? I have 2 zeros. There's 2 zeros because this is a 0 and this is a 0. This one has multiplicity 2, and -4 has multiplicity 3. And the multiplicities add up to the degree of the polynomial. Let's look at another one. And oops, you can see I forgot to make it look like x cubed there, so that was a bad graph. Let's look at another one. I have -2 times x plus 2 and x minus 4 squared. So first thing I look at is the degree. So invisible 1, that means the degree is 1 plus 2, which is 3. Odd. So the ends go in opposite directions, and since the leading coefficient is negative, that means as x approaches infinity, we'll be going towards negative infinity. So we'll be going down and up at our ends. We have 2 zeros. This 0 has multiplicity 1, so -2. And the 0 at 4 has multiplicity 2, 1, 2, 3, 4. So this one's going to cross. This one's going to touch. Now we need to figure out where it crosses the y-axis, because this one didn't just so happen to go through the origin. So I just plug 0 in. -2 times 2 times -4 squared gives me -4 times 16, -64. So we're going to put that way down there. So we start up here. We cross the axis. We reach this point. We come up, we touch, and we go back down. And again, calculus will teach you how to make it look better. Let's see. It looks like I graphed the wrong thing there. I'll have to fix that picture, because that one's touching at -4 and crossing at +2. So I graphed x minus 2 and x plus 4 squared. I'll fix that. Oh no, that's this picture. No, it's not. Okay, that's all right. Any questions? Okay, we'll look at one more just so we do one that happens to have even multiplicity, even degree. 3 minus x. Now this one was a little tricky. I purposefully made it a little tricky. You need to acknowledge the fact that 3 minus x is the negative of x minus 3. So this one has a hidden leading coefficient of -1. Degree is 4. So both ends go down. It crosses the x-axis at x equals 3, and it crosses the x-axis at x equals -4. Here it crosses it and it looks like a line. Here it crosses and it looks like a cubic. So I'm going to plot those 2 points, 1, 2, 3, 1, 2, 3, 4. And to figure out where it crosses the y-axis, we just plug 0 in. So we have f of 0 is 3 times 4 cubed. Not going to do that one off the top of my head. Cleared out the old stuff. 3 times 64 is 192. So it's way the heck down here at 192. Chances are you'll be expected to label these important points on your graph. You'll also be able to label maxes and mins. So the ends go down. We know it's going to come up here, and 192 is a positive number. It's way up high, not down low. So it comes up, and at -4, it crosses like a cubic. So let's make it flatten out. Comes up here, and then just goes flat down. Now, again, you can see that the max of this graph occurs somewhere over here. I didn't know that. Yeah, the graph in the document is wrong, Gage. I typed the wrong thing in. I'll fix it and repost it and send it back out to you. Thank you. So, questions about graphing polynomials?
I do. How do you know where that max is going to be? Like you said that you didn't know that it was over. I guess that a little bit.
Oh, calculus is going to teach you where the max is. So that's what's coming. You're going to set your derivative equal to 0, and that's going to tell you where that max is going to be. So you're going to learn that in section 4.4, I believe it is, when you get to shapes of graphs.
Okay.
Yep, something to look forward to. Yeah, I plugged in the 0 to get the 192. That's where it crosses the axis. But the max isn't actually at 192. It's somewhere to the right of it. But using pre-calculus skills, we had no way of knowing that. So right now we're just graphing things as if we don't know calculus. And then you're going to get to make better graphs next week. Okay. Exponential functions. And if you want some more practice, Paul's online math notes are always really good for stuff. Graphing exponential functions. Important things to know about exponential functions. Is how to spell them. Exponential. The domain is all real numbers. They always look either whee like that or woo like that. They're pretty boring. If you have just e to the x or a positive base to the x, then you're going to have a horizontal asymptote equal to the y-axis. y equals 0. The x-axis. Geez. Logarithmic functions have a vertical asymptote at x equals 0, the y-axis, but exponential functions have a horizontal asymptote equal to the x-axis. And usually what we do is we shift them, we flip them, we stretch them. So that's where you end up with f of x equals a times b to the x plus c. The horizontal asymptote is right here at c. The sign of a tells you whether you live above or below the horizontal asymptote. If a is positive, then you're above the horizontal asymptote. If it's negative, then your graph is below the horizontal asymptote, and it will never cross its horizontal asymptote. It's either completely above or completely below. B will tell you about the end behavior. So let's look at one. One half of 3 to the x minus 2. So step number one, if you want to graph this thing, is to dash in that horizontal asymptote at y equals negative 2. Our leading coefficient here is equal to 1/2. That means I'm going to live above the horizontal asymptote. To figure out where we cross the x-axis, the y-axis, we can plug 0 in. 1/2 of 3 times 3 to the 0 minus 2. So 1/2 minus 2 is negative 3/2. So we're going to cross right there. And since this is a positive 1/2, it lives 1/2 unit above that horizontal asymptote. Now we just need to figure out what else is going on. Well, since this is a number, our base 3 is greater than 1. That means the limit as x approaches infinity of our function is equal to infinity. And the limit as x approaches negative infinity is equal to the horizontal asymptote. So my graph looks something like this. We could figure out where it crosses the x-axis if we wanted to, just to get an even better graph. Then you would let 0 equal 1/2 3 to the x minus 2. So 2 is equal to 1/2 of 3 to the x. So 4 is equal to 3 to the x. So x is equal to log base 3 of 4. And you could get a decimal estimate for that and figure out where you want to cross the axis. And it would be somewhere right in there. Questions? F of x is 2 times 4th to the x plus 3. So here's my horizontal asymptote. Positive, so my graph lives above the horizontal asymptote. And this number is between 0 and 1, which means the limit as x approaches infinity of f of x is equal to my horizontal asymptote, and the limit as x approaches negative infinity of f of x is equal to infinity. So we already know exactly what this thing looks like. Horizontal asymptote at 3. 1, 2, 3. The y-intercept is going to be 2 units above the horizontal asymptote. 1, 2. It's going to approach the horizontal asymptote, and it's going to go off to infinity. And yeah, looks something like that. Questions? Okay. Just for completeness, you know I have to do 2 that live below the horizontal asymptote. F of x is negative 2 to the x plus 5. So it's going to be below a horizontal asymptote is y is equal to 5. 1, 2, 3, 4, 5. Now it lives below, and I usually just go ahead and I look at this number and I think about what it would do if it lived above the horizontal asymptote. If it lived above, it would go like this. So by living below the horizontal asymptote, it's going to go down, and this is going to be 1 unit below. So we look something like that. And again, you could figure out what this point is by setting negative 2 to the x plus 5 equal to 0. Now, the only thing calculus is going to be able to tell you is concavity on these, because you don't have maxes and mins. Chances are when you have to graph something with an exponential, it's going to be combined with another function. Equals negative 2 times 1/2 to the x minus 6. So horizontal asymptote below horizontal asymptote, and the y-intercept is 2 units below the horizontal asymptote. Negative 6. 1, 2, 3, 4, 5. 6, so it's going to live way down here. Crosses the axis 2 units below. Now, if it lived above the x-axis, since my base is a fraction, it would go this way. So since it lives below, it goes the opposite way. So instead of approaching positive infinity, as x approaches negative infinity, it approaches negative infinity, but as x gets bigger and bigger and bigger, it still approaches its horizontal asymptote. So does that help with exponentials? Feel a little better about those now?
Definitely.
There's the pretty picture. And I found a Professor Dave Explains video for that one. He's always fun to watch. Now let's talk about logarithmic functions. They all have that same shape. The important thing about logarithmic functions is you cannot log negative stuff. So you have to figure out the domain, and chances are you won't have something as simple as the just log base A or natural log of X. It's going to be natural log of something. So you have to take what is inside that set of parentheses and set that greater than 0 in order to figure out your domain. But the domain of just plain old log is 0 to infinity. Can't natural log or log 0, and you can't log negative stuff. All log base A functions cross the axis at 1. So the x-intercept is always 1 because logs are exponents and x to the 0 is equal to 1. And the vertical asymptote is the y-axis, and it approaches negative infinity as you approach 0. So as x approaches 0 from the right, the log goes to negative infinity, and it always passes through the point A1 because, again, logs are exponents and a to the first power is equal to a. Not going to graph those, they're just review. Questions about log functions? Okay. Let's see. Looks like rational ones are next. Yep. And we talked about these a couple of weeks ago, but it's always good to do a quick review. So first thing you do with a rational function is look at the domain. The domain of rational function, and by a rational function, I'm talking about simple rational functions where you just have a polynomial sitting on top of a polynomial. So the domain is everything except where the denominators are equal to 0. So you take that denominator, set it equal to 0. Those are the bad guys. They're not allowed to be in the domain of the function. So let's start with x squared minus 3x minus 10, living on top of x squared minus x minus 20. So factor two numbers whose product is 10, whose sum is -3. And then two numbers whose product is -20, whose sum is -1. 4. So I notice that I'm going to be able to cancel those things. But just because I can cancel it does not mean that 5 gets to be in the domain. My domain is everything except 5 and -4. Every number that is excluded from the domain is either a whole or a vertical asymptote. So this is something that you should remember from limits. At 5, we have a removable discontinuity. We have a whole. And at -4, we have an infinite discontinuity. We have a vertical asymptote. So I'm going to dash in my vertical asymptote at -4. 1, 2, 3, 4. Now, we always know about end behavior for rational functions. You can look at leading coefficient over leading coefficient, and you know what the limit as x approaches both positive and negative infinity, since the degree of the numerator is the same as the degree of the denominator. These are both going to approach leading coefficient over leading coefficient, which is 1. Okay, so what else do we know? Well, we have a whole, a removable discontinuity right here, and the way we find its location would be looking at the limit as x approaches 5 of my original function. But to do that, you would look at the limit as x approaches 5 of this simplified version of the function. And you would just plug 5 into that. So you would get 5 plus 2 over 5 plus 4, which is 7 over 9. So at the point 5, 1, 2, 3, 4, 5, it's going to be at about 7 over 9, and you have a little hole there. That's your removable discontinuity. Now you can figure out your x-intercepts by setting the numerator equal to 0. You know that your function, your original function, looks exactly like the function x plus 2 over x plus 4, except that it has that hole there. Well, we've already created the hole, so now we can just look at what I like to call f sub s of x, a simpler function, x plus 2 over x plus 4. So finding the x-intercepts, we set x plus 2 equal to 0. So x equals -2. And finding the y-intercept, I plug 0 in. 0 plus 2 over 0 plus 4. 2 over 4 is a half. So here was 1. And I can play connect the dots. Now, if you need to, you can make yourself a sign chart to see where this other piece lives. But you can just really use your smarty brain to figure that out, because you know that it has to approach this vertical asymptote. You know that it has to approach this horizontal asymptote, and you know it's not allowed to cross this axis. So you can be like a detective and just figure it out. Questions? There's the pretty picture. The rational function again. We have x minus 2 squared over x plus 3 times x minus 4. So x cannot be equal to negative 3, and x cannot be equal to 4. And both are vertical asymptotes because nothing cancels. Horizontal asymptote, you can be real calculus fancy and think about the limit as x approaches infinity, or you can just be pre-calculus, look at the leading terms. Degree of the numerator is the same as the degree of the denominator, so it's boring. It's just like the last one, leading coefficient over leading coefficient. 1 over 1 is 1. We can find our x-intercept by setting the numerator equal to 0. So I know the point 2, 0 is on my graph. Y-intercept by looking at f of 0, so 0 minus 2 squared over 0 plus 3 times 0 minus 4 gives me 4 sitting on top of 3 times negative 4, so negative 1/3. So now I just dash in my asymptotes. I have one at negative 3. I have one at positive 4. I cross the axis at negative 1/3, the y-axis. I cross the x-axis at 2. And I have horizontal asymptote at 1. So now I just have to figure out how I connect these dots. And now calculus is going to help you with this one because it will help you figure out exactly how these things look. But we can just connect the dots. We know we have to go down towards negative infinity. And we didn't cross here because the multiplicity of that 0 was 2. So it has to look like a parabola when you're very close to that 0. And then these have to live up here because they're not allowed to cross the axis anywhere else. Questions?
Just a quick question for the horizontal asymptote. So pretty much if the numerator is 1 and the denominator is 2, that just means it's 1/2. It goes towards 1/2.
Yeah, if I had a 2 sitting down there, so if I just had x minus 2 squared over 2 times x plus 3 over x minus 4, then your horizontal asymptote would be 1/2. If you had 5 times x minus 2 squared over x plus 3 times x minus 4, then your horizontal asymptote would be 5. If you had x minus 2 sitting on top of x plus 3 times x minus 4, then you would have degree 1 on top, degree 2 on bottom. So your horizontal asymptote would be the x-axis. And if you had it upside down, more x's on top than you have on bottom, then you have no horizontal asymptote. This one would be a slant asymptote. So if you have a higher degree up top, then you look at the first terms and your end behavior will behave like whatever polynomial you end up with when you look at the first terms. For example, if we had something that started with ax to the n plus a bunch of stuff over bx to the m plus a bunch of stuff, then your end behavior is the same as a over b n minus m. So if n is bigger, then it's going to be like a polynomial. If n is smaller, it's going to go to 0. If n and m are the same, then it's just a over b. That always works. Other questions? Okay, you're going to have lots of radical functions and rational exponents in your questions. So just as a reminder, let's talk about the domain of radical functions. So one up here. Let's just make it bigger. There we go. So simple radical functions. If the index is even, then your radicand must be positive. Chances are you're not going to have one that's just the square root of x, because you know the square root of x, x has to be greater than or equal to 0. So you take whatever is underneath that square root and set it greater than or equal to 0 to get your domain. If the index of the radical is odd, then all real numbers, you're good to go. And let's see, here's the pretty pictures. If we have an even index, let's turn that one off. There's the square root, fourth root, sixth. It just gets flatter and flatter. If you have an odd index, then it just looks like that cubic function flipped around the identity line. So there's x to the 1/3, x to the 1/5, and you can see again it just gets flatter and flatter, but it always keeps that little S shape. Now, finally, trig functions, the ones that seem to baffle the students the most. First thing, you need to know the domain and range of your trig functions. The domain of sine and cosine is all real numbers. The range of sine and cosine is -1 to 1. It never gets bigger than 1. It never goes below -1. It changes if you multiply something on the outside, then that will stretch it. If you multiply it by a negative thing, it flips it upside down. For inverse functions, inverse sine and inverse cosine, the domain of the inverse is the range of the original function. So the domain for those two is -1 to 1. But in order to have an inverse, we had to limit the domain. So for sine, your inverse function will always be from -π² to π² and not -π². I will fix that and send you the fixed one too. So -π² to π². -π² to -π² would be really boring. For arc cosine, it's always 0 to pi. And sine and tangent are buddies. Their inverse functions have the same ranges. Cosine and cotangent are buddies. They're the cos. Their ranges are the same. They go from 0 to pi. And that's because sine, you get all of the outputs of sine on the right side of the unit circle, and you get all of the outputs of cosine on the top of the unit circle. That's why we use those for the range of the inverse. Tangent, your range is all real numbers, and cotangent. Those are both all real numbers, but they have a lot of vertical asymptotes. Tangent has a vertical asymptote everywhere that the denominator is equal to 0. The denominator is cosine. Cosine's equal to 0 anytime you have a pi k multiple of pi/2. So pi/2, 3pi/2, 5pi/2. Every time you circle around that unit circle another time, you get another 0. Cotangent has sine on the bottom, so it's not defined anywhere that sine is equal to 0. So 0, pi, 2 pi, 3 pi, 4 pi, all of the multiples of pi. Secant and cosecant, well, secant and tangent have the same domains. Cotangent and cosecant have the same domains because tangent and secant both have cosine in their denominators. Cotangent and cosecant both have sine in their denominators. The range of secant and cosecant is the opposite of the range of sine and cosine. Sine and cosine go from -1 to 1. Secant and cosecant take everything else. -infinity to -1 and 1 to infinity. And then the inverse functions, the domain of arcsine and arcsecant and arccosecant is everything except the domains of sine and cosine. So -infinity to -1 and 1 to infinity. Just the opposite of those. And then their ranges are the same except the bad guys are removed. So the range of secant is the same as the range of cosine, except it's not allowed to have pi/2 in it. And the range of cosecant is the same as the range of sine, except it's not allowed to have 0 in it. And I made you a Desmos graph if you want to play with some of these. This is actually just sine and cosine, and you can see how different numbers change things. If we change A, it stretches it. If we change B, which lives inside the parentheses, that changes the period. If we change C, which is inside the parentheses but next to the X, that's going to shift them left and right. And if we change the D, that's going to shift them up and down. So all of these things we expect you to just kind of know already, and I'm sure that you may have forgotten some of them, so that was why we reviewed all of this today. Let's see. And that's it. Any questions on anything?